Welcome back, chemistry students. Dr. Tellis here. Continuing on with alkanes. You can tell that a sponge is saturated with water because when it's squeezed, the water pours out. When something is saturated with water, it already holds as much water as possible. Compounds called hydrocarbons, which contain only carbon and hydrogen, can also be saturated, but not with water. Saturated hydrocarbons are hydrocarbons that contain only single bonds between carbon atoms. They are the simplest class of hydrocarbon. They are called saturated because each carbon atom is bonded to as many hydrogen atoms as possible. In other words, the carbon atoms are saturated with hydrogen. If we were to think of ethane, that's 2 carbons. Each carbon we know has 4 possible bonds. And if it's bonded to a carbon, like it is right here, that means every other bond is a hydrogen. So it is saturated with hydrogen. So an alkane is a saturated hydrocarbon. We can also have cycloalkanes. They are cyclic, so they're in a circle. They are also saturated hydrocarbons that form another homologous series with the general formula of CnH2n. So this is a little bit different because when we had a straight chain, it was CnH2n plus 2. In this case, the carbon atoms are joined in a ring. Let's look at the first option, C3H6. So we can see if it's 3 carbons, 3 times 2 is 6. Here's our ball and stick model. We can see that there are 3 carbons in a circle, and it is called cyclopropane. So meth-eth-prop, and it's ane, that means single bond. So each carbon still has 4 bonds, 2 to hydrogen here, 2 to other carbons. We can also have 4 carbons, and notice that the 4 of these bonded together make cyclobutane. 5 carbons, cyclopentane. 6 carbons, cyclohexane. I think you get the idea. Let's move on to look at the nomenclature of alkenes and alkynes. These compounds are said to be unsaturated since the carbon atoms have at least 1 non-single bond. The rules are essentially the same as those for alkanes, except that names end in "ene" for alkenes and "-ine" for alkynes. The general formula for an alkene with 1 double bond is CnH2n, so similar to that cycloalkane. The position of the double or the triple bond needs to be indicated in the name by bond position number. Let's look at this guy. We want to find our longest parent chain, and in this case I would say this is our longest parent chain. It does involve the double bond. We need to number our parent. We want the branch to be at a low number, but when I have a double or a triple bond, we want that to become the lowest number on the carbon chain. So that precedes the branch. The branch was the number 1 most important thing when numbering an alkane, but when we have double or triple bonds, we then want to number with the bond being closest to the smallest number of carbons. So I'm going to name this carbon 1, 2, 3, 4, 5. So there are 5 carbons. We know that's pent. There is a double bond, so that will end in ene. Where is that double bond? It's after carbon 1, so we would say 1 pentene. Great. Now we need to tell where the branch is. It's a single carbon, so it's a methyl, and it's off of carbon number 3. And notice when I write, I start with the parent name, and then I figure out that it's a double or a triple or a single bond, so figure out that ending, and I work backwards. So I often get a little messy, and for my final answer, I would rewrite it so that it was in a straight line. But as you can see here, the name is 3-methyl-1-pentene. Notice between numbers and letters, there's a dash. Again, letters and numbers, there's a dash in between. Let's look at a few more alkenes. We can see here that they are already numbered this parent chain, and that there are 4 carbons with a double bond, so we know that it is butene. If we numbered it, the double bond would be after the 1, so we would just say 1-butene. Here we have the longest parent chain. When you don't lift up your pencil, is only 3 carbons, so that would be propene. Now with propene, you don't actually have to say 1 propane. I don't think it would matter if you did, but if I had 3 carbons and I had the double bond right there versus if I had the same 3 carbons and I had the double bond there, that's the only 2 places that the double bond could be. And I would always number closest to the double bond. So 1, 2, 3 or 1, 2, 3. The only option is 1 propene. They just leave off the 1. Then we can see that off of carbon number 2 we have a methyl group. So this name is 2-methylpropene. Then we get to these 2. Let's look at the difference. I have 4 carbons in a row and I have 4 carbons in a row. But notice that these CH3s are on the same side and these CH3s are on opposite sides. So while they both have the double bond after carbon number 2, so they are both 2 butenes, the ends that are on the same side we say are cis 2 butene. And notice that these ends are on opposite sides, so we say trans 2 butene. Why don't you pause the video here and try to draw structures for the 6 possible alkene isomers with the formula C5H10, and then give the name of each. Let's look at the 6 different ones. You could draw 5 in a row with the double bonds being right after the first one. That name would be 1-pentene. This is drawing it showing that the H's are not just going to be up and down. It's showing it more that in real life, the H's want to be as far apart from each other as possible. Same with the carbons want to be as far apart as possible. So it's not just going to be linear like this. This is the easiest way of writing it. This is going to be more realistic of what the compound looks like. We could have the double bond after the second carbon. And when it's after the second carbon, we could have it in 2 different ways. We could have the first carbon down, and then the second carbon, the double bond after the second carbon, third, and then have cis 2-pentene. So we know that this is 2-pentene. We could also have trans 2-pentene. So we could have the first carbon down, and then after the double bond, the second 2 carbons up. There's still 5 in a row. There's still the double bond after the second carbon. It's just we could have this first carbon could be up, and then these second 2 could be up, or the first carbon could be up and the second 2 carbons could be down, or vice versa. So we have a cis 2-pentene and a trans 2-pentene. We could also have 4 carbons in a row with the double bond being after the first one, and on the second carbon we could have a methyl group, so 2-methyl 1-butene. We could also have the methyl group be off of number 3, and we could have the double bond for the butene be after number 2 with the methyl group being on number 2. If you try drawing it some other way and think, wait a second, what about this one? I'll bet you if you flipped it around that you would have one of these 6. So it is probably an isomer of one of those. And then we have alkynes. Alkynes have carbon-carbon triple bonds and have the general formula of this, CnH2n minus 2. So C2H2 is F. We know that there's meth is 1 carbon, F is 2 carbons. If N is 2, then 2 times 2 is 4, minus 2 is 2, so C2H2. You don't need to worry about the common name. The common name is acetylene, but we would name this 2 carbons is F. Because it fits this formula for the triple bond, it's ine, ethine. Like alkanes, alkenes and alkynes are colorless. The low molar mass compounds are gases, whereas compounds with higher molar masses are liquids or solids. Alkenes and alkynes have an elaborate chemistry. Because they are unsaturated, the carbons are not linked to 4 other atoms like in alkanes. In alkenes, however, each carbon atom linked by a double bond is bonded to only 3 atoms. If we were to look at a double bond, let's say carbon double bonded to a carbon, this carbon right here, since it has 2 bonds right there, it only has 2 others. So this carbon has 1, 2, 3 atoms that it's bonded to. In alkynes, each carbon atom linked by a triple bond is bonded to only 2 atoms. So in this case, this carbon atom, if there is a triple bond, then it's bonded to this atom and a second atom. So in alkynes, each carbon atom is bonded to only 2. It's possible to increase the number of groups attached to a carbon atom in an alkene or an alkyne by addition reactions. And this is where molecules with the general formula XY, such as hydrogens, halogens, hydrogen halides and water, add cross the carbon-carbon double or triple bond. So in this case, notice I have an alkene, right, a double bond. When I add this halogen, Br2, notice that it breaks that double bond. So instead of carbon only being able to be linked to 1, 2, 3 other atoms because of that double bond, it breaks that double bond. So this carbon can now be bonded to 4. One bromine will come off of that one carbon, and the second bromine will come off of the second carbon. Same with if I have a triple bond. Notice I have a C triple bonded to a C, and I'm going to add 2 chlorines. So that triple bond is going to go down to a single bond, which means that this carbon can bond to that H and 2 other chlorines. So this carbon can take a Cl2 there, and this carbon, in addition to that H, there's the H, can take 2 chlorines there. This then becomes 1, 2. So this is carbon 1, this is carbon 2. There's 2 bromines, so we say dibromo. And because there's 2 carbons, it's ethane. It's now a single bond. Here I did have ethine, but now after adding those 4 chlorines, I have 1, 1, 2, 2 tetrachloroethane. Here's some more addition reactions with more complex compounds. You can see here that there is a double bond between the second and the third carbon, and when I add Cl2, what's going to happen is that double bond is going to go down to a single bond, and I will have a chlorine there and a chlorine there as shown. And then I have this complex compound, but again, if I have a Br2 added to it, it's going to find where that double bond is. It will break that double bond off of that carbon, and off of that carbon is where those bromines will attach. The same is true when fats are hydrogenated with hydrogen. Here I have propene. Again, it's going to take where that double bond is, break that double bond when I add H2 to it. So therefore, another H will come off of that carbon, and another H will come off of that carbon. Peanut butter has partially hydrogenated vegetable oil. Can you draw the structure of the compound obtained when Br2 is added to propene? Try that and name it. So here's how I drew it initially. I drew propene, so I had 3 carbons and I had the double bond. Again, it wouldn't matter if your double bond was after the first carbon or after the last carbon, it would still be the same. Just make sure that each carbon has 4 bonds, and when that double bond is there, there can only be 2 other hydrogens. Then when I add Br2, it's going to break that double bond, making that single bond there, so I can have a bromine coming off of that first carbon and a bromine coming off of that second carbon. It doesn't matter if you put the bromine on the top or bottom, if they're the same, if they're not, because we know that this bond can move and bend. So that Br on top could just as easily flip and rotate and be Br on the bottom. We would then name it 1,2-dibromopropane. Let's look at some aromatic compounds. Benzene, which is C6H6, is a key molecule in chemistry. It is the simplest aromatic compound, a class of compounds so named because they have significant and usually not unpleasant odors. Here I have 6 carbons in a circle, so this is a cyclo, but notice that there are some double bonds. Every other one is a double bond. So this carbon right here still has 4 bonds, 1 to a hydrogen, 1 to another carbon, and a double bond to another carbon. And because of that, this carbon then has 1 bond there, 2, 3, and then 1 to a hydrogen. So there's 1 hydrogen for every carbon, because each carbon has a double bond essentially coming out of it, because this one has that double bond, 1, 2, a third to the next carbon, so the 4th to a hydrogen. Benzene, or C6H6, has 2 resonance structures with alternating double bonds. Here I can have a carbon double bonded to a carbon with a single bond to this carbon and an H. But that double bond could just as easily be flipped down here. Notice that every carbon there's a single and a double coming out of it. This carbon has a single and a double. This carbon has a single and a double. It could be either way, and those double bonds are delocalized over the ring. They could always be switching, which then allows us to represent benzene with this hexagon and the circle inside of it. So notice how we have a hexagon with the double bonds one way, and then another hexagon with the double bonds on different edges. So we can simply write it as a hexagon with the circle in the center. And that just shows it could be either one of those. Let's look at how we can name benzenes with different things attached to it. So in this case, here's my benzene ring, and I've got, let's say, a chlorine coming off the top. That would just simply be 1-chlorobenzene. What about this guy where I have my benzene and I have a methyl group on top and I have a methyl group coming out of the bottom? Well, there's two ways I could name it. I could name this as my first carbon, so 1, and then count either to the right or to the left. It would be the same. 1, this would be carbon 2, this would be 3, this is 4. So 1, 4 dimethylbenzene. Or I could say, assuming that this is 1, and then down here would be para. So you assume that there's something coming out of wherever the 1 position is. And then if you say para, there's also something coming out 3 spots away from it or in the 4th position. So we would say para dimethyl. So there's 2 methyls. 1 methyl coming out of the top, 1 methyl coming out in the 2nd, 3rd, 4th spot of it. It's not ortho, it's not meta, it's para, and then benzene. Let's look at these. Here I have a benzene ring, and I have 2 chlorines coming off of it. It doesn't matter if I were to call this carbon 1 and then this carbon 2, or if I started the other way around and this was carbon 1 and this was carbon 2. Either way, it would be 1,2-dichlorobenzene. Or I could say that it is ortho-dichlorobenzene. Because again, if you say ortho, that means, okay, there's something coming out of here, but there's also something coming out of where that first position. So ortho means that there's something from that top position as well as to the right of it. And di tells us that there are 2 things indeed. Chloro says that there's 2 chlorines, and then we have our benzene ring. For this one, I've got my benzene ring, but here I have a methyl group and a methyl group. So I could say 1,3-dimethylbenzene. Or if I have something coming out of the 1 and the 3, I could just say meta-dimethylbenzene. And here, when I have NO2 groups coming off of something, here I'm looking at the cheat sheet I gave you for this chapter's practice problems. If I have an NO2 group, we say nitro. So in this case, I could say 1, 2, 3, 4. So I could say 1,4-dinitrobenzene or para-dinitrobenzene.